Okay, so now I'm going to talk about the idea of subdivision. And if you're familiar with numerical computation, say of PDEs, then you might have heard of the term of mesh refinement, right? So if you have, for example, a computational mesh, you want to make it finer. It's like in order maybe to minimize the error. And so you want to be able to do something similar now. It's like, but in the context of simplicial complexes. Okay, so this naturally leads to the idea of what is called subdivision. So a simplicial complex L, okay, is a subdivision of another simplicial complex K if two things are true, if the underlying spaces are the same, so the K and L underlying spaces are the same, and every simplex L is fully contained in a simplex in K. All right. So that's basically the idea. It's like, I mean, again, the way to sort of think about this is something like the analog of mesh refinement, where you take a mesh and maybe you subdivide or you break up. It's like a cube into smaller cubes, right? So one way to construct a subdivision is by what is called barycentric subdivision. Okay, and the way to sort of think about it, the reason why it's called barycentric subdivision is because the barycenters are going to play an important role in this construction. Okay, and I'll explain it's like how you go about constructing this subdivision in two ways, and maybe one is sort of more accessible to you. Okay, so anyway, so I denote this by saying L is SD, the subdivision of K. All right, and this is based on, again, introducing new simplices, it's like which include or which involve barycenters of simplices. Okay, so this is based on sort of the introduction, on introducing sort of the barycenter of a simplex. Okay, which is just the average of the vertices. Okay. Okay, so let's look at an example of that. So let's say we have sigma, which is in the simplicial complex, and it's a k-dimensional simplex, I denote it by sigma k. All right, so it's the convex hull of, say, u0 to uk. All right, so the barycenter of sigma k then is in some sense just the average of the points. Okay, so you have k plus 1 point, so you take 1 over k plus 1, right, the sum of the ui's, right, I goes from 0 to k. Right, so you can actually put this k plus 1 inside, right, so this is really just the sum from I equals to 0 to k, 1 over k plus 1 ui. So at least in the local barycentric coordinate system, which just involves the simplex sigma k, right, that just means that the barycenter is the one where all the sort of barycentric coordinates are equal to each other, and still satisfy the normalization condition, so it has to be that it's 1 over k plus 1. Okay, so that's what's called the barycenter. Okay, which again is just the average of the vertices. Okay, so now I'm going to give you two possible ways of thinking about the barycentric subdivision. Okay, and again, keep in mind that I'm going to introduce, it's like new vertices, it's like which are barycenters of, various simplices in the problem. Okay, so let's see what happens. So I'll just leave the definition of the barycenter here for now, and then I'll erase it in a little bit. So, so this is going to be done inductively, at least as one approach. So we proceed by induction on dimension. Okay, so I'm going to define the subdivision, the barycentric subdivision of the zero skeleton, which is of course just the vertex set, as being just the same thing. So at this stage, I'm not introducing new vertices. I'll do that later on. Okay, and the way to sort of see this, another way to sort of see this is that if you're just left with vertices, individual vertices, then the barycenter of an individual vertex is that vertex itself. So I'm not doing anything when I do the barycentric subdivision of just the zero skeleton. Okay, so anyway, so once I have that, sort of induct sort of the initial part of the induction, then I can consider the following. So if I'm given a barycentric subdivision, of the sort of the lower skeleton of, say, the j minus 1 skeleton, right? We can construct the subdivision of the k skeleton by first adding the barycenters of each of the j simplices and then I want to connect them to the subdivided boundary of the j simplices. So I should say to add the barycenters as new vertices and connect it to simplices on the boundary. Okay, that subdivide the boundary. Of the J simplex. Okay, so that might be a little bit hard to digest, so let me sort of try to illustrate this construction with a worked example of, say, just the barycentric subdivision of a 2 simplex, which is of course just a triangle. But hopefully this sort of at least gives you a flavor for what is involved. Okay, so this is a worked example. So I consider a 2 simplex. Okay, so K is just this thing, right? If you prefer, it's like maybe let me try to explicitly draw it as vertices, edges, and then something inside it. Okay, so maybe that's an easier way to see it. Okay. Okay. Now, so what they're first saying is that we look at the zero skeleton, which of course are just the vertices, and then SDK0 is just the vertices. So SDK0 is just the original vertices. So I'm not doing anything to it. Okay. I guess I should say K0 is that first, and then SDK0 is again the same thing. So I've not really done anything here. Okay, so now let's look at K1, right? So K1, right, are these. and then I look at SDK1. Okay, all right. So what's happening, okay, is that first I look at the one simplices, which are these three edges, and then I append new vertices, which are at the center, at the barycenter of those edges. Okay, so I have the original ones, this, and this, and maybe let me try to label it with a different color. So I have new 0 simplices, which come from the barycenters. Okay. And then I'm not quite done yet because I want to then connect these. It's like two things which subdivide the boundary of each edge, right? So given an edge, the boundary are these 2 points. So I need to connect the new barycenters to the boundary of the corresponding it's like edge. So I have to add these things here, right? So, all right, so these are the new barycenters. And then this is obtained by sort of connecting sort of the barycenter to sort of boundary of the one simplices. Okay, so I said new barycenters associated with one simplices, right? Okay, all right. So maybe I'll move this a little bit to the side here so I have a bit more space. Okay, so then there's K2. So K2, of course, is the full thing. All right. Okay. So hopefully you understand what I'm doing here. Okay, so I look at SDK2. All right. So SDK2 is everything we had before, right? So you have this, this, and this. These points here, and these edges. Okay, actually maybe I'll just write them all in black so that you know that that's from the previous stage. Okay, so I'll just draw them all in black so that I know they're from the previous stage. All right. So, okay, so now first I have to add the barycenter of a 2 simplex. Okay, so my convention is blue for that. So there's a 2 simplex here. It's like in the barycenter is say there. Okay. And the next thing I want to do is I want to connect the barycenters to the vertices on the boundary of the 2 simplex. So there are 1, 2, 3, 4, 5, 6 of these. So I will add these. Okay. And I also want to connect that barycenter to edges which are on the boundary. Okay, so I'll do one more color here. So hopefully you get to see what I'm doing. Okay, so hopefully it's clear what's going on here. Right, so I've added, you know, 6 new, it's like edges. I've added 1 vertex, and I've added 1, 2, 6 triangles, right? So this is the barycenter, sorry, the barycentric subdivision of the 2 simplex. Okay, so again, this is sort of just the triangles, sort of connecting, which sort of comes from connecting barycenters sort of to boundary edge of the 2 simplex. Sorry, Not sure you can see that. Okay, so again, it's like these are the boundary edges. It's like of the 2 simplex, right? And I'm appending that Barycenter to this. Okay, so that whole thing now is the barycentric subdivision of the original 2 simplex. So there's another way to sort of see this, right? So if you look at maybe if I could try to blow it up. Right, so actually let me just look at this green triangle there, right? You can check that this green triangle is obtained, is a simplex which is spanned by the following. It's the barycenter of the 2 simplex, it's plus the barycenter of this edge, plus the barycenter of this vertex, okay? So it goes from dimension 2 to dimension 1 to dimension 0, okay? And with the property, of course, that, this this 2 simplex, right, has this edge as a face, and this edge has this vertex again as a face, right? So there's this inclusion relationship, if you will, it's like which is satisfied. So this naturally leads to another way of constructing the barycentric subdivision. So let me look at a few more examples. So you see this red edge here is the barycenter of, again, the 2 simplex with the barycenter of the edge, right? It doesn't have to go all the way down to a vertex, right? So it could be the lower dimensional things as well. So again, you can hopefully you can see that this gives you an alternative characterization of the barycentric subdivision. Okay, so alternatively, right, given sort of a nested sequence of simplices. Okay, so sigma 0 is a proper sort of face of sigma 1 and so on all the way up to sigma k, right? And this is in k, right? We associate to it a simplex which is obtained by the convex hull of the barycenters of these simplices in that sequence. Okay, so Bary sigma 0, Bary sigma 1, all the way up to Bary sigma k. All right, and then this will be in the barycentric subdivision of the complex K. So I should say that there is no need, it's like here, okay, so these are all proper faces, but there's no need for you to go down to a vertex on the one end. There's no need for you to start with a top dimensional simplex. There's no need for the dimensions between sort of adjacent simplices in this nested sequence. It's like to differ by only 1 in dimension. Okay, so for example, you can go from the barycenter of this 2 triangle to the barycenter of just that vertex. So that's a dimension 2 and that's a dimension 1, and it corresponds exactly to this edge here. Right, so all these things are possible. So again, hopefully you can convince yourself by looking at this picture that every single thing it's like you have in that barycentric subdivision of the original 2 simplex is of this form here. Okay, so yeah, so this gives you again a nice alternative characterization of the barycentric subdivision, and maybe one or the other is sort of easier to understand for you. Okay, so let me then say a few more things. It's like primarily having to do with the idea of how refined, if you will, it's like a barycentric, or how refined a simplicial complex is in terms of how fine the mesh is, if you will. Okay. So so the diameter of a set in Euclidean space is just the supremum over distances between 2 points in that set. Between its points. Okay, so that's sort of a fairly intuitive notion of a diameter, it's like of a set. Then the mesh of, or if you prefer the mesh size, okay, so the mesh of a complex K is the maximum diameter of its simplices, right? Of any of its simplices. Okay, and it's easy to convince yourself that this has an alternative characterization just in terms of the length of edges. Okay, so because the diameter, it's like of a simplex, is really just the maximum of the edge length over all the edges in the simplex. Okay, so or equivalently, the length of its longest edge. Okay, so so there's a mesh lemma which has to do with the idea of what happens if you start with a simplicial complex with a particular mesh size and you apply barycentric subdivision to it, how that decreases. Okay, so I will just state the theorem and I won't prove it, but we'll use at least the result later on. Okay, so the mesh lemma is as following. Okay, so if delta is just the mesh size of a simplicial complex, then the mesh size of its barycentric subdivision, okay, is going to be bounded from above by d over d plus 1 multiplied by the original mesh size. So again, for any finite dimensional complex, right, you'll have this multiplicative reduction, it's like in the mesh size each time. Okay, where of course d is the dimension of K. All right, and I'm going to omit the proof here, but it is in the book if you're interested. Okay, anyway, so so this gives you you know, some information about how you can subdivide meshes, and the basic idea is that that's going to be necessary. This sort of, you know, mesh refinement or barycentric subdivision is going to be necessary in order to guarantee that you can construct approximations of continuous maps which are accurate enough in some appropriate sense. So I will stop here for now.